Hello guys, welcome back. Uh, this morning, we are going to continue our intermediate machine learning from Kaggle. So we are going to discuss, I'm trying to discuss about cross-validation. So we're just gonna read here through and let's see if we can do the exercises, okay? So we learned to use cross-validation basically to better measure for our model performance. Remember, there's another technique to measure the model performance, which is to use the to divide between the data set, between the training and the validation, right? And this is, I think, another way to further fine-tune how good is our model. But let's see what's kind of the differences or the similarities. So it says here, machine learning is an iterative process. You will face choices about what predictive variable to use, what type of models to use, right? What arguments to supply to those models, and so far, right? So the argument is like the whether in the algorithm there are different kind of parameters that you can put. For example, I think on the random forest you can put the algorithm. I think or the sorry on the how to treat categorical variable. um, Whether you want to convert it using one-hot encoding, and then you can put the parameters as so replace the text into a mode or a median or something different or just zeros, right? So there are different parameters. Um, what predictive variables? I'm not sure what is this referring to. So far, you have made these choices in a data uh, driven way by measuring model quality with validation, yeah, or a holdout set. Okay. But there are some drawbacks to this approach. To see this, imagine you have a data set with 5,000 rows. I'm just gonna make it this bigger. Probably it's better. There you go. So you have 5,000 rows. Okay, imagine there's 5,000 rows. Um, and then you will typically keep about 20% of the data as the validation data set, as we always do in our previous exercises. So there's 1,000 rows for the validation process. This leaves some random chance in determining model scores. Um, that this model might do well on one set of 1,000 rows, even it will be inaccurate on a different 1,000 rows. Oh, okay. So I think it happens if you choose the 1,000 rows that are quite good in quote, and then when you validate it, and then you get a good result, but you're just kind of lucky because, for example, um, what if all of the 1,000 rows is just so happen that like you're shuffling a deck of cards, right? Ideally everything is kind of random, but there's a good chance that when you give out the cards to a person, that person will get all the aces or all, for example, all the Jack Queen King kind of, right? It's kind of unlikely, but it could happen, right? So at an extreme, you could imagine having only one row of data um, oh, in the validation set. If you compare alternative models, which one makes the best prediction on a single data point will be mostly a matter of luck. Okay. In general, the larger the validation set, the less randomness, right? Noise there is in our measure of model quality, and the more reliable it will be. Okay. Unfortunately, we can only get a large validation set by removing rows from our training data. And smaller training data set means worse model, right? So because when you have a smaller data set, then it means you only have a smaller sets that you can take out from that training data set, right? So, and then what if you get all of them? That's the one that's kind of biased, right? So what is cross validation? So in order to do that, we want to introduce this called technical cross-validation. Basically, we run our modeling process on different subsets of the data to get multiple measures of model quality. And then probably we can average it. For example, we could begin by dividing the data into 5 pieces. It's 20% of the full data set. So for experiment one, you get 20% at the first, let's say the first 20% of the total data set. Experiment two, you get the validation at the second, like 20%. Or you can kind of take it randomly, but I don't know. In this case, we say that we have broken the data into 5 folds. Okay. So this is the first fold, the second fold, third fold, fourth fold, and fifth fold. Then we run one experiment for each fold. Okay, so in experiment one, we use the first fold, just in one, as a validation, as a holdout, and everything else as a training data. This gives us a measure of model quality based on the 20% holdout set. In experiment two, we hold out data from the second fold, so here, and we use everything except the second fold for training. The holdout set is then used to get a second estimate. We repeat this process using every fold once as the holdout set. Putting this together, 100% of the data is used as a holdout at some point. So it's kind of like more like evenly distributed. So the idea is to use 100% of the data as a holdout, right? That's the idea. And we end up with a measure of model quality that is based on all of the rows in the data set, even if we don't use all rows simultaneously. So that's the idea. So should you use cross-validation? Cross-validation gives a more accurate measure of model quality, which is especially important if you are making a lot of um, modeling decisions. However, it can take longer to run because it estimates multiple models, right? One for each hole. Like in this case, you have to because it's divided into 5 folds, you have to like run it 5 times, right? In order to utilize 100% of all the data as a holdout data or as a validation data. So given this trade-off, when should you use this approach? For small data set where extra computational burden isn't a big deal, we should run cross-validation. So for a larger data set, a single validation set is sufficient. So you don't have to do this probably for a full data set because it takes a long time and it takes kind of like expensive to do it, right? Um, and then your code will run faster and you may have enough data that's little need to reuse some of it for holdout. There is no simple threshold for what constitutes a large versus small data set, but if your model takes a couple of minutes or less to run, it's probably worth switching to cross-validation. Okay. Alternatively, you can run cross-validation and see if the scores for each experiment seem close. If its experiments yield the same result, a single validation set is probably sufficient. Okay. So now we're gonna do the example here, just some code. So we'll work with this with the same data as in a previous tutorial. Um, we load input we load the input data in X and the output data in Y. Well, we define a pipeline. Remember what pipeline is? Pipeline is basically kind of a compilation of a library that executes a sequence of function. That's what a pipeline is. So, for example, if you want to uh, create a pipeline of, let's say, post-processing, right? So, because remember, before you can even put the data set into the algorithm to train it or to fit it, you have to post-process, means you have to take out some of the missing values, take out the rows or sorry, the column that has no, let's say, sales output, if sales is like the Y or the output that we want to predict. Um, we want to also to treat uh, um, the the categorical values, how to convert it, right? We want to use whether it's just drop the whole thing, right? Just forget about it, the most simplistic thing, or you want to use label encoding or health encoding. In encoding, there's a sequence of things that you have to do. In one hot encoding, you also have a sequence of what things you have to do. For example, the uh, uh, investigating whether it's the cardinality of the features or not, right? Cardinality is basically the number of unique values for that specific features, because you don't want, for example, given the constraint, the budget, of course, constraint, you don't want to include all of the number of unique values. And then you also want to make sure that the unique values that are on the let's say the training and the validation is they are completely the same, right? Instead of one of them is like it has only 5 unique values, and on the validation it does not it has only 6, then it doesn't work. So there's a lot of little things that you have to taken care of, right? And all of those little things that you can sequence it because they're kind of like always in a process. You have to put it in a process. You cannot like just do it like in a manner that not consistent. So you can put all of those things into the pipeline. That's what the pipeline does, right? So so we define a pipeline that uses an imputer to fill in missing values and a random forest model to make prediction. Uh, while it's possible to do cross validation without pipelines, it is quite difficult. Using pipeline will make the code remarkably straightforward. Okay, so we're using pipeline, and then I think after the pipeline, we can do cross validation. So we're gonna import the algorithm, right? The one that we want to use. We are importing the pipeline. We are importing the simple imputer, which is basically getting rid of the missing values, and then put it into something else, whether it's a mean or the median or a mode or something else. So over here, we're creating the pipeline, and then we created the steps, right? First, you want to um, in a preprocessor, you want to put a simple imputer algorithm, and then the model we want to put the random Ferris regressor with specific parameters over here. That's done, and then we obtain the cross-validation score using cross-val score algorithm from scikit-learn, and we set the number of folds. So we just call this function, right, cross-val score, and then we you want to multiply by -1 over here, since sklearn calculates negative MAE. Okay, so to make it positive, you want to I don't know why is it okay, -1 plus cross validation score. Um, yeah, okay, and then you create the um, put in the parameters. So you put the my pipeline here. Oops, right, which is defined by this guy basically. Um, and then the X, the input, and then the Y, and then the fold is the number of fold 5, and then uh, I'm not sure about this negative mean absolute. I think this is the algorithm to compute. Yeah, so this thing will kind of automate the whole thing. This um, cross validation score itself, I think it's kind of it's a kind of a pipeline because it does several things in a consecutive manner. For example, it will put everything the one in a pipeline. So um, that's already compute the pre-processing compute also has the placeholder for the algorithm, and then we'll take the input and the output, right? And then we somehow will uh, automatically divide that into five uh, data folds for the X, right? And then so it will compute all of those things like automatically over here, this thing. And then somehow it will, after that, it will put it in the algorithm, put it in the, sorry, in the pre-processing first, make sure the data set is clean. And then after that, we'll put it into the next sequence, which is the algorithm, the random forest regressor. And then we'll train it, right? We'll train it. So it will get um, uh, a new, a train algorithm, and then using that train algorithm will automatically um, compute the negative mean absolute error um, using five times because there are five folds. Um, so that's kind of cool, and everything is going to be just computed there. Yeah. So and then you'll generate kind of five different mean absolute error over here, and then you kind of pick the best, kind of, I'm not sure. Yeah. So so the scoring parameter chooses a measure of model quality to report. In this case, we choose negative mean absolute error. The document for scikit-learn show a list of options. It is a little surprising that we specify negative MA. Um, Scikit-learn has convention where all metrics are defined, so a high number is better. Oh, okay. So a high number is better. So in this case, this is the best one. Okay. Because the metric is a negative one. Okay. Because this is a negative mean absolute error. Okay. Okay. So the higher the number, the better, I guess. Using negative here allows them to be consistent with that convention, though negative MA is almost unheard of elsewhere. We typically want a single measure of model quality to compare alternative models. So we take the average across experiment. Okay, so we take the average, scores mean. Okay, okay, so then you got this the average here. Okay, using cross-validation yields a much better measure for model quality, with the added benefit of cleaning up our code. Note that we no longer need to keep track of separate training and validation set. Okay, so especially for small data set, it's a good improvement. Okay. Wait, I thought for small data set. Yeah, okay. This is kind of recommended for small data set because in a big data set, you kind of have a well, you have first where you have more data set and you have more. The assumption is you have more a diverse city in that data set, right? So you are unlikely kind of the probability to get a bad data set. It's unlikely because it's more diverse, right? Okay. So we are gonna put this on our next exercise. Okay. Click this. Come on, come on. Let's go. Let's go. Let's go. Let's go. Let's go. Let's go. Okay. Cross validation. Preparing. I'm just gonna see this if I can. Sharing private. GPU off. Yeah. I'm just gonna do it public probably. That. Save. Yeah, it's kind of slow because I think I'm using the computer is kind of old. This is a MacBook 2015, I think. Although it's a MacBook Pro, and I'm using OBS, so it kind of slows down the whole thing. Yeah, I don't know if there's a better alternative. Probably if I use QuickTime, but then there's no webcam, so I cannot show kind of my face. I don't know whether that's better or it doesn't matter. But anyway, it's kind of working, but it's just kind of slow. I notice when I try to run the kernel, so or run these, yeah. So what is a kernel? Kernel is basically uh, a specific type of working environment. So like this, right? This is it says preparing for kernel. So this kernel is for Python, right? And has um, like certain like packages already kind of pre-installed in it, and it's working on the cloud. So I think kind of that's the definition of a kernel. I'm not sure, but I know it's a specific environment that has multiple libraries that's running underneath it, right? So it's kind of specific. So for example, this is probably using Python 3.6 instead of 3.5. I'm not sure, but it's kind of specific. And then it has like a NumPy pre-installed. There's probably has a sklearn already pre-installed. So you can just, you can just type the instruction import, right? I think Rachel from Kaggle has a nice kind of a summary what is a kernel. But from my point of view, it's just kind of an environment where you can do coding uh, um, on that environment, right? Without having to kind of install um, all the stuff, right? Otherwise, it's going to be very complex. You have to install this, install that, and then you have to like on kind of like take care of the version. You have to remember and keep track of the version. I don't know why is this taking so long. Um, yeah, this is kind of weird. I don't know why it's taking so long. Probably I should open another one. Let's see. Let's see. Can I open another one? Um, Make sure. Okay, it's on the correct Wi-Fi. Yep. Yeah, you're kind of slow. Probably I should stop first the recording and then continue it after this. Okay, I'm just gonna stop it first.